yesterday, we saw that there are 14 maskable core interrupts particularly, and it goes through a logic of latch switch and using a global switch for triggering a particular interrupt into your microcontroller. And we saw that flag bit is for storing your particular values, and IER switch is there in order to prevent the nesting of interrupts, so that if one interrupt service is happening at the same time, another interrupt should not be causing any trouble, so that your main operation should performed in a better way. So it does not clearly mean that you can service, like only one interrupt and that's it. It is not like that. Concurrent, I mean, after one task has done, another task will happen, since parallel processing is not possible over here. So it's like that. Another thing we saw is interrupt enable register. In this interrupt enable register, we saw that it is a 16-bit register and all the interrupt bits are over here. And we saw how we can use this, OR and logical AND operation in order to enable any interrupt or in order to disable any interrupt by setting ones or zeros bits into this particular register. So this is how any register is going to program. Like you can put your values into hexadecimal or decimal as well. If that register is there to store value from your integer from 0 to certain amount, if it is a counter, or if any counter is there, you can put your values from 0 to, if that is 16-bit counter, 2 to the power 16, that much integer value you can put into that register. So but if it is a bitwise like this, you have to program it into ones and zeros only. So this we saw yesterday. Then we saw this is a global switch interrupt enable interrupt global mask bit, that is INTM bar. It's active low, particularly active low switch, in which if you put 0 it will be enable, if you put 1 it will be disabled. So there was a peripheral interrupt expansion module, as we saw yesterday, that main 12 interrupts, it is subdivided into 16 subgroups, and it is connected through the same logic of IFR, IER, and global switch. So right now we have 192 interrupts with the help of this peripheral interrupt expansion module. And then we have looked at pi assignment table, that is pi vector table, in which there are certain groups and subgroups as well. And then we saw how we can select particular group and subgroup in order to select particular interrupt. Okay. And this was the extension of that particular table, as we saw before in the first slide, as 16 could not accommodate over here, so they have shown it over here. So we saw how to trigger these particular interrupts with the use of groups and subgroups. After that, this was about the pi register, that is peripheral interrupt expansion module registers. And in these registers, we saw one is IFR register, which is which is varying from x equal to 1 to 12 for 12 groups, I mean to say, and there will be 16 subgroups over here. So you can see that 16 subgroups you can trigger like this, that if you put 1 into particular subgroup, it will be on. If you put 0, it will be off. And then we saw there was one acknowledge register, which should be there after the every interrupt service routine has happened. Like if any interrupt service routine you are writing a code, you need to write this acknowledge dot all instruction into that particular interrupt service routine. So yesterday I did not talk about interrupt service routine. Interrupt service routine is a kind of function which is to be executed after interrupt has happened. So whenever you are triggering any interrupt, there will be one ISR loop running, that is interrupt service loop running. So it's like a switch button. Like after some time you are switching on something, and then again it is happening, you're switching on something, and then again it is happening. So it's like a periodic interval that your ISR is running. So you can say that it's certain, or another example you can take into account, that if certain dog is coming to your house and you're feeding to him every day at the same time. So it's kind of like that your clock will be serving to the interrupt, and whenever the interrupt is calling, that particularly that ISR will be executing that loop. And the ISR loop is responsible for writing any code, or execution of any code. So whatever you are writing in the ISR loop, okay, that will be your one particular separate function, and it will be running your algorithm along with your main loop. Okay. So then you have en pi register, that is enable pi. It should be there because in order to enable your peripheral interrupt expansion module, since it's a completely different module which is connected to your core interrupt logic, you need to give a separate instruction that is enable pi in order to turn it on. This was about yesterday, and this is the overall flow of interrupt signal. which we can see from here that if you trigger any interrupt to flag and enable register, then you have a core interrupt logic. After that, any interrupt which is from x dot y group, that is group and subgroup, it's selected from this pi vector table. And after that, you can see that default isr.c is a, it's kind of API, application programming interface. We'll see in the code what is it exactly mean and why it is required. So after that, any interrupt will be served when this once this interrupt is called from this pi vector table, your ISR, that is interrupt service routine, will be served. So whatever box you're seeing here, it's a kind of interrupt service routine block which will be servicing this interrupt at every periodic interval. So this information is very much required in order to generate any algorithm. And once you understand this interrupt, it will be very easy for you in order to model your own algorithms. Because once you know, you can take an example. Like I can give you an example. Let's say you are injecting a certain signal uh, into your board, and it's a periodic signal, okay, with the help of ADC. So it is repeating after a certain period of time, and now you want to do certain operation into that signal. So with the help of ADC, if you call an interrupt, what will happen is after certain interval of time that interrupt will come, and whatever operation you want to perform with that signal, where you want to reduce your duty, where you want to increase your duty, that you will be able to do in your interrupt service routine. So once you understand interrupt, it will be very easy for you to model any one of your algorithm. And many people have already worked on this controller. So a lot of help will be available to you as well. If you're going to code on your own, like TIE2E forums, as I said yesterday, it is available, and you can post your doubts onto that forum if you have any doubts while coding. But make sure that you have read the technical reference manual throughout, or you have attended any particular course, so that it will be easy for them as well to understand what exactly you're saying. So this was about it. Then we saw about Watchdog timer module. As I told you, Watchdog is a kind of it's a kind of uh, security guard which is watching whether your algorithm is working properly or not. And there is one inbuilt counter, 8-bit inbuilt counter, that is, it can count from 2 to 0 to 2 to the power 8. So it's a 8-bit counter. So in that counter you can see that you, if your clock, that particular your main clock of your CPU, if it is servicing regularly to that counter, then it's fine, that counter will work well, easy and fine. But if certain issue is there with your main clock and it is not able to run, then obviously your program will interrupt. But in case if certain let's say certain issue is there in your algorithm as well, this watchdog counter will not receive the clock from your main CPU, and then it will reset, and it will not cause, and it will not allow your main algorithm to run. We'll see how this watchdog interrupt is triggered in the example as well, and then you will understand better what I was saying. So, and then we'll look at the APIs today. Okay, why these APIs are important, and what is pi control, pi vector. Okay, so after that we'll go for EPWM module as well. So I hope this is clear to you all. Is there any doubt in this session? Till now, what I said, is there any doubt to anybody? Okay, fine. So I guess everything is clear to everybody, and everybody has well understood what I've said. So I'll consider this thing, and I hope you have watched all the previous lectures as well, so that whenever I'll be going to explain anything to you, you guys would be clearly able to understand what I mean to say. So, so let's see how you can import first all the examples if you do not have a board, or if you do not have a resource explorer access. Like if you have resource explorer access, we saw yesterday that you can download your examples from here, from here. But if you do not have it, then then also it is possible for you to import your example, so that you can see if my screen is visible. Okay, so from here you can see, if you go to file, as I said yesterday, you can click on import. After clicking on import, if you go to Code Composer Studio, and you can see CCS projects. So if you go to CCS projects and browse, then it will immediately take you to your workspace. Okay, so instead of workspace, you can go into C2000ware software, and then you can go to, okay, from C2000ware software, you can see all your examples would be listed over here. So from device support, if you go to F28790, then you can go to examples, and if you go to CPU1, you can see from here different examples are listed. So you just have to select any particular folder and then click on select folder, and you can import your example. Since I have already imported some of them, I can see whether I can import it or not. Okay, so ADC SOC PWM, I can import it like this. Okay, so it is kind of that. You can see that you can easily import your example like this in CCS. One more thing we saw yesterday, how do we create a new project? So if you go on new and click on CCS project, you can create your new project. But during with this process, what will exactly happen is, if you are creating your new project with this as well, you have to do many things, like you have to add your header files, you have to add your main APIs as well. And after that, if your header files location is not proper, what will happen is you will continuously face errors when you will be running your code. So in that case, I would suggest you to go with the resource explorer, where what will happen is you will be provided with an empty project. That empty project you can use in order to make your own algorithm. Like let's say if I go to this F28790, and this is the simple way in order to create your project. If you want to create new project, that is also possible, but because of location error, if your C2000 ware is not at particular location, or let's say what your CC studio is not at the same location, you will get many errors. Your header file should be accessible from that particular project. Then your API should be proper, then your out dot bar file should be created. So to all that, different errors you will face. So in order to do that, CCI is provided with you a empty project. So if you use this empty project and you import it, since I have already imported it, it's showing me error, and I have used it for a Blinky project. So in this one, Blinky CPU01 is there. I have renamed it, or maybe this kind of example is there given to you, and you can see all your APIs over listed over here. And in the main algorithm, you have to make all the changes. So this is the main algorithm, and this in this main algorithm, you can see it's written void main void your main function, and everything else is empty. So you can write your code here, whatever you want to start variables you first declare, you declare any function, you call any function, and you try to write your own code. So before creating or before writing into this, like barely, it will be very difficult for you, and I do not as well expect from you that you write your code like this only. But first, before learning into that, you must understand the flow of any algorithm. So how to understand the flow of that algorithm, how does it flows, and how exactly it happens, that I'll explain in a bit. Kindly wait for 2 minutes. This enter your search term, this thing is coming in my laptop. I'll just close it once. Yeah, so I don't know why this enter your search term box is coming in my laptop. So we'll see today one API one by one, what actually any application programming interface means, what is your main code, and how it is linked to certain other APIs. And then we'll see an example of Watchdog timer that I told you. So this was one project that I created yesterday, that is STTP. And this is another project, timed LED blink, which is I imported from the C2000ware. So this timed LED blink was a toggling of any particular LED, and it was related to red LED. So I've created the same project named as STTP for triggering the blue LED. So we'll see that as well, how exactly I have reached to that particular thing. So from here, first we'll see about this timed LED blink project. From here, yeah. So before looking into this, I will explain one by one what are all the APIs mean. Okay, so we'll start with system control. So this system control API, instead of showing into this presentation, I will directly tell you over here. This system control API is actually deals with all the clocks of your particular CPU. Whatever clock is there in your particular microcontroller, all the settings, all the initialization of that particular clock is there into this system control code. So from here you can see, as I told you yesterday, that there is your launchpad name F28790. Then you have initialization of system phase lock loop, in which your external oscillator, this is an instruction in which your external oscillator is divided by a PLL loop, and it is dividing here by 2, so that your clock operates on so that your microcontroller operates on particular clock of 200 megahertz. As I said before, that this particular microcontroller has two core CPU, CPU1 and CPU2, which works on 200 megahertz of clock frequency. So it's a you can say it's initialization for that particular thing. After that, you can see all the peripheral clocks in the sense, if your EPWM peripheral is there, if your equip peripheral is there, if your recap peripheral is there. So this is initialization of all that peripheral clocks. So it's a predefined function like clear screen we saw. So in this predefined function you can see what is written. So in this particular function you can see from here, if you just put your cursor onto that, this thing will appear. So from here you can see that your CPU timer 0, 1 and 2. So all these clocks has been enabled. This PCLKCR0 is actually peripheral clock control register 0 bit of CLA1 control law accelerator, which you are turning it on. Similarly, this is peripheral clock control register 0 CPU timer register. CPU timer 0, timer 1 and timer 2. Three timers are given. See, basic difference between your timer and counter, if you understand well enough, is that your counter will be serviced by your main clock of your CPU, and your timer will have its independent clock. Okay, so it means that if your counter is there in your inbuilt module, that has to be serviced by your CPU clock, so with certain clock dividers or something. And timers will be independently running of your main CPU clocks. It will be not dependent on your main controller clocks. That's what I want to say. After that, you have HRBWM module, that is high resolution pulse width module I said. This is also a peripheral, so it's peripheral clock control register 0. After that, you can see this is time-based clock synchronization. We'll see what this instruction exactly means. Okay, it's used for all the time-based module synchronization in a particular EPWM module. Like it's something like that when you are having multiple EPWM modules and you want all your pulse to start at the same time in order to prevent the phase. You have to set a correct phase shift into two PWMs, right? So what you want is you want all your PWMs to start at the same time. So for that, synchronization is there. So all that instructions are related to that. You can see EPWM peripherals as well, ranging from 1 to 12 modules. So that is in the control register too. So it is also a peripheral clock. So what I want to say basically is this initialization of system control, it all deals with the clock signals of all your microcontroller, ADCs, comparator, DACs, and every other module. So this is one of the API. So this API is mandatory in your every algorithm whenever you run, that you initialize all the clocks of your particular microcontroller. So you can see in your main project as well, if you go here, this first instruction is there, which initialize system controls, which includes PLL, Watchdog. It will enable all your peripheral clocks, and this example function is found in F28379D system control.c file. So this example function, in the sense, this is the function that you're calling, predefined function that you're calling, and all the things related to this predefined function are into this particular API, which is system control.c. So I hope you have understood this. Is it clear to all? Is it clear to everybody what I said?
Yes, sir.
Yeah, okay. So I think you can understand now what I've said. So through this, what is exactly happening is, through every particular instruction, you will understand how exactly code flows and why we are writing these APIs. So there won't be any confusion regarding these APIs in your mind, that this application programming interface, all these algorithms, why we are unnecessarily running, So this is a kind of system. So every code, whenever you are going to write, you have to initialize all the system controls. So this will be your first code of your line. Okay. And it will be mandatory for all your algorithms, and this you have to write into your main file, main function. That's what I meant to say. After that, uh, yeah, after that we'll go into this pycontrol.c register. So pycontrol.c is a peripheral interrupt expansion, as I said yesterday. So whatever the initialization of that particular pycontrol register, okay, it is necessary if you are using interrupt into your algorithm. So this pycontrol register and your pyvector particular register, this you need to initialize in order to run any particular interrupt. First, if you go to pycontrol.c, these are the header files. Header files has to be include, as I told you before, that header files include the declaration of any predefined functions if it is there, like we saw that standard input output.h and conio.h. These are the header files in which the declaration of printf, scanf, and your getch and clear screen function is there. So those header files are necessary in order to run those predefined functions. So these header files are also necessary in order to run your examples, and if any other functions are there related to your device. So those header files declaration will be over here. So in this one you can see, in this particular code you can see all the header files over here. So if you just click on this, you can see ADC defines .hr here, CAN defines .hr here, EPWM defines .hr here. So all the header files, even if related to system control defines .h, if you go, you can see from here that all the symbols which is related to your system control will be defined over here. And if you go to epwm defines.h, so this is a header file related to epwm. So whatever inbuilt instructions are there for epwm module, that we'll see. So you can use this instruction which has this particular bits already stored. So if you use this instruction, so whatever it is defined to, or whatever it is assigned to do any task, it will do that particular task. Like if you have to trip zone, if you want to enable or disable, you can use this particular. Trip zone is for protection of your EPWMs. If you want to make your EPWM pulse to get off at certain period of time, then you can use this trip zone as well. We'll see what does it exactly means. Then you have a chopper duty. Chopper, as I said yesterday, it is used to uh, you know okay, we will go into that thing later. So this is about system control, and this is about header files, as I said. So all the header files will be listed into this, and it is necessary that you include all these header files into your project. But one more thing I would like to tell you, that these header files are nowhere but into your C2000 ware software. So into your C2000 ware, if you go to device support and F23790 headers, path is shown over here, so it will be included over there. So if you sometime create your new project or something and you want to include certain header files, You can as well go to right click it. You can go to show build setting, and from this show build setting you can go to include option. And from this include option, if you want to include certain header files, the path is shown over here. You just have to click plus sign. After clicking this plus, you have to go and browse. Or if you directly have a directory path which is from certain other algorithms that you have copied, you can directly put it over here, and you can put OK. That is also fine. Okay, so this was about including your header files. So I do not recommend, I suggest you to touch this portion, because if you try to do this, there will be many errors, because what happens is this particular software is designated so that it will take the examples from C2000 ware only, and it is mostly related to C2000 ware. So whatever header path, include path is there, so it should be accessible for this particular software in order to get all those header files and include files from your C2000 ware. So that's why they have given you this empty project, which I told you before, so that you can make your own code into that particular thing. Once you have done that, what you can do is I'll tell you one more way. If you're really interested into this, you just go to show in local terminal, and you go to system explorer. Okay, so if you go to system explorer, it will tell you the location of this particular project. Now if you open this, you can see there are certain files, which is one is ccs project file, .c project file, .p project file. This is cpu1 ram file, which is cpu1 active. This all the object files and everything is there. Object file we saw yesterday, it is generated after once compiler has executed your code. So all the files related to that particular code would be over here. And let's say if you want to create any new project, like I have created HTTP yesterday. So what I have done is I have just copy and pasted all the things from this timed LED blink to my HTTP folder, and I have created one new file into this. And what that new file is just main.c. All other APIs, if you just right click on this, go in show in local terminal, and if you go to system explorer, so this will show you the exact location of that particular API. So if you click this, it will directly take you to the C2000 ware. So you can see here it's nothing but a text file in which all the codes are written. So this has to directly come from your C2000 ware. So that's why I do not recommend you to add any source file on your own and then try to run your algorithm. It will be really difficult for you, because it is designated to take the files from C2000 ware. Okay, so most of the people, they read the manual and they try to create their project on their own, and if they try to fail that, they face many issues. So one other way to go with this, that to create with new project, is you just create your new project from here. Let's name it anything. Click on empty project.c and you finish it. Once you finish this, what I suggest you is, there's one already main file over here, but you can see in hash include only compiler files are there. It is not inherently taking C2000 ware file. So if you try to, forcefully try to include that C2000 ware, you will face many errors. Why it is like that? Because I have downloaded this Code Composer Studio into local disk D, and I have put C2000 ware into local disk C. So my workspace location and my downloaded location is different. So that's why also it may happen, or there are certain other issues as well. So in this case, what you do is you just go to your HTTP, and what you do is, if this project is over here, you can just Control A, Control C, and you can just put it over here. One main file is there related to CCS project and everything, but you can see CPU1 RAM file is not here, which was there for responsible for generating any particular code. So you can just Control A, Control B over here. It's asking me to replace. You can replace easily. Okay, then those will be available into your main file. Okay, so if I replace the files in the destination, so if I click on this, okay, you can see CPU1 RAM file is over here. So now maybe I'll be able to run this code, whatever if I write over here. Just like this, I have created this HTTP code yesterday. Okay. So right now I'll delete this as we don't need it. So you can see over here that this is timed LED blink code. Okay. So from this code, do not change any API. If something happens, then this API will also leads to an error. So we were talking about APIs before. So this was about pi vector table API, in which you can see all the interrupt service routine, all the predefined variables related to interrupt service routine are declared over here. EPWM1 to EPWM12, then you have SPI, DMA, direct memory access, then you have SCI, ADCs, control law oscillators, peripheral interrupt expansion, interrupt IPC, then you have pi over here. So all the ISR which you can use in order to run or in order to cause any interrupt and run your particular code are listed over here. So this API is also there. If you are going to use interrupt, this two APIs, which is pi control and pi vector.c, it is necessary. Then you have IPC.c. This API is not needed for this particular algorithm because it includes interprocessor communication module support function. So in this one you can see that if you want to use two or more microcontrollers together, you can go for this. So this comes into that particular mode. So let's not look into this right now. After that, we have Gpio.c, that is a Gpio module support function, general purpose input output. In this one, we saw yesterday, like if you want to initialize all the Gpio pin functions, you can use this particular API, or even if you are using any Gpio, okay, you need to put this API into your code. Okay, it is necessary because you are using any Gpio pin, like in this LED blink code, we are using a Gpio pin because we saw yesterday from the presentation that from this you can saw it is a GPIO 31 blue LED and GPIO 34 red LED. So this is a GPIO pin only. So in order to run your algorithm for that particular GPIO pin, you need to have this API as well. After that, you have interrupt service routine. So this is necessary. So I'll explain this a little bit. You can see that the functions name which are there into this default ISR block, it's already there. The definition of these functions are already there. So these functions are predefined functions. You can see from here, one is interrupt void timer to ISR. So it's a text nothing, returns nothing type of function, and it belongs to a interrupt service routine serviced by timer 2, CPU timer 2. Similarly, there will be timer 0 and timer 1 as well. You can see from here. So timer 1 is shown over here, timer 2 is shown over here. Then you have other certain defined functions interrupt. You can see these are the user one. In the user one, if you want to even change this function, you can change it. It's for your use, and you can write your own function as well. Okay, so once you will understand one code with the interrupt, you will able to understand what this exactly is. So these are all predefined functions are over here, which are related to any particular interrupt. So this default isr.c is an API in which all the functions related to your interrupt service routine are defined over here. Wake ISR is there, which is related to your watch wake interrupt. Then you have EPWM interrupt trip zone interrupt service routine. So whenever any EPWM is also causing any interrupt, okay, it will directly come into an interrupt service routine, and you are allowed to write this interrupt service routine directly into your main code so that you can write your particular code or algorithm into this block. Okay. So this should be your understanding whenever you are going for writing any algorithm. So you can see all the interrupt service routine which are there. It's listed into this particular API, whether it is ADC, whether it is PI reserved, whether it is CLA, whether it is auxiliary system clock or ADC. All the interrupts would be given over here. So you understand interrupt service routine and interrupt as well. Now, next instruction shown to us is DI interrupt. DI interrupt is given in order to disable all your interrupts. As I said yesterday, Before setting all the interrupts, you need to clear all the unnecessary bits if there are certain bits into certain registers of interrupt and you don't want that to cause any malfunction to your particular algorithm. So what you will do is you will it is a core instruction DINT. So it will directly have access to all your interrupt registers and it will clear all your interrupts and it will initialize. And in order to initialize your pi control, you need to use this predefined instruction, that is initialize pi control. So this will be there in all your algorithms. Okay, whatever procedure I'm telling you into main till certain time, I'll tell till where it is. So this should be all present in your main algorithm whenever you're writing your algorithm. Okay. Then to clear your core interrupt, you have to as well clear your interrupt enable register, interrupt flag register, so that if flag is having certain bit ones or zero, it should be clear. So writing zero to every register will clear all your interrupts. And once your initialization and clearing is done, you can as well initialize your pi vector module, because it is necessary, as you know that why we are using pi vector module now. So all this initialization is very necessary whenever you are running any code. So whenever you are doing initialization means you are telling them that your algorithm is ready to on, you are going to execute something. So that way you understand. So that way, that's why this initialization is necessary. Then this we'll talk about in 2 minutes. First, before that, this particular instruction is using CPU timer interrupt. Okay, so why this CPU timer interrupt? There is no particular reason as such. Okay, you can use CPU timer 0, 1, 2, any interrupt for your own use. Okay, since it is also doing a service to interrupt service routing, you can use this interrupt. But there is one particular instruction in order to cause this interrupt after a certain period of. I guess some student is coming. Please hold on a minute. Okay. So this instruction of initialization of CPU timers, if you go to cputimers.c API, okay, from here you can see that all your timers have been initialized, like CPU timer 0, 1, and 2 as well. So you can see here, right now CPU timer 0 interrupt count is 0. Okay, we'll see key what does this means. Okay, I just want to say you that this is the initialization of all the CPU timers. So it is necessary that when you are using any interrupt which is triggered by your CPU timer, you need to initialize all the CPU timers. Generally, people use interrupts through EPWMs, ADCs, or CPU timers. Okay, or trip zone, whatever you want to use. So CPU timers is a general way because CPU works at a 200 megahertz of clock frequency. Okay, so whenever this 200 megahertz of clock you are working at, it gives you maximum clock frequency. So the time which is required in order to execute your ISR, it will be very less whenever you are using CPU timers as an interrupt, because you can maximum operate up to 200 megahertz clock frequency as well. Okay, so it is like this. Another thing is, I should have explained to you about CPU timers before, then it would have been easy for you to understand. Okay. Best part we'll see first. That thing we'll see in 5 minutes. From here you can see that timer interrupt 0 in the pi module. Okay, okay. Before that, this instruction is there. GPA mux 2. This we saw yesterday. I guess I've explained this, that if you are using port A mux 2, okay, then you can trigger to GPIO 31 pin. Okay, so for port A mux 2, it will be ranging from 16 to 31, and for port B, it will be from 32 to onwards, like 63, another 30 pins, as we saw. And every port is divided into mux 1 and mux 2, we saw yesterday. And there is one direction register which is belonging to port A. So this direction register, what it is doing is it is setting that LED to an output. From here we saw. So what we are doing here is we are setting an LED to an output and we are initializing GPIO 31 as a general purpose input output pin. So this instruction is particularly to initialize your GPIO 31 as general purpose input output pin. If you do certain other things over here, if you put it 1, okay, And if there is any EPWM assigned to this particular GPIO, it will act as a EPWM. So put it one here, it won't be working as a GPIO pin. Okay, it will be working as a EPWM if it is dedicated to that particular thing that we saw from yesterday into that presentation. From here, as you know, that if any GPIO is allocated to any other particular mux value, so in that way, it will be assigned to any particular peripheral. So here we are operating it as a general purpose input output pin. So I'm initializing it as general purpose input output pin. After that, this direction register, as I said, it is to set your LED as output so that whatever is there, you can see it from the your board. Okay. Then you have here interrupt enable register. Okay, this is M is related to enable. Okay, whenever you are using D, it is related to disable. Whenever you are using M, it is related to enable. So what I'm doing with this instruction is I'm enabling this interrupt one group. Okay, so if you want to interrupt two groups, if you want to interrupt three group, you can do like this. Okay, so you don't have to change anything over here. I'll suggest you that if you want to assign any particular interrupt to any particular core group, which is from 1 to 14, you can directly put it over here. So M stands for enabling your instruction, and this is logical OR operator, which is saying that your interrupt enable register is enabled with this particular instruction. Okay, so if you want to enable any particular group and subgroup, you can choose over here. Then you have a pi module, as we saw yesterday, that pi 1, it means core interrupt 1, and it is belonging to subgroup 7. So main group is from pi, after pi instruction main group is there, and after this x7 it's a subgroup. So 1 cross 7, we can see into the table. So from here, yeah, so from here you can see this 1 cross 7, it belongs to timer interrupt 0. Okay, so timer interrupt 0 in the sense CPU timer 0. So basically we are triggering CPU timer 0 interrupt with this particular instruction, and this is to enable your interrupt 1 group. I hope this is clear to everybody. After that, these two instructions are there to you are enabling your global interrupt with EINT, and these two instructions should be there in order to enable your global interrupt switch INTM. Okay, so you have to put it whenever you are writing your code. So these instructions are there, and it should be there whenever you are running your code, because if you're triggering any interrupt, you can just change your group and subgroup. Okay, all rest of the things should be as it is. You don't change anything else. Okay, if you want to make any changes as well, if you want to write your own functions as well, you write it in sub functions. Main functions you are not allowed to do anything. Main functions should include only initialization of timers and clocks and everything. I hope this is clear to everybody. Is it fine?
Yes.
Okay, so how exactly this code is running? Okay. So this is configure CPU timer. See, whenever anything you're writing into this particular microcontroller, if it's coming in certain color, let's say blue or anything else, any color, pink or whatever it is. If it is coming in any color, you always think that it is a predefined instruction. Predefined instruction in the sense, like whenever you're writing scanf, you have to write percentile D, and then you have to declare ampersand, and then you have to write your variable that you are taking it from the user. So basically it will be predefined. The format of that particular instruction will be predefined. Similarly, this instruction, which is a predefined instruction, that is configure CPU timer, is related to your CPU timer configuration, CPU timer 0 configuration, in which you are writing ampersand and then you are writing CPU timer 0. It means you are calling CPU timer 0 register, which is working at 60 megahertz of clock. You can increase this up to 200 megahertz as well, and it means that after every 500 milliseconds, okay, if you want to increase this, if you want to decrease this, you can change it, but you can consider 500 into 10 to the power 3. Okay, so 10 to the power 3, you separate it and you just put 500. So if you want to put basically this particular thing is in microseconds. Okay, so whatever you will put over here, it will be in microseconds. So if you multiply it by 10 raised to power minus 6 and 10 raised to power minus 3, if you keep aside, what will happen is it will be resulting in 500 milliseconds. Simple mathematics. So according to this, after every 500 millisecond, your CPU timer 0 interrupt should be serviced. Okay, so in that way, what will happen is at the clock rate of 60 megahertz, where every clock will be having time period of 1 by 60 mega. Okay, that will be the time period of that particular clock which is servicing this CPU timer. And in that particular clock, you can say after 500 millisecond, you're servicing an interrupt. It means certain clocks will be passed in that 500 millisecond time. And after that, one interrupt is servicing. Understood? Because 60 mega is a lot. So for that, your time period will be very less. So your one clock will be of very less time. And in 500 milli, you can see there are numerous clocks will be served. And after that particular 500 millisecond, you are basically triggering an interrupt. And that interrupt is calling which function? Your CPU timer 0 function. You can see ampersand is for calling that particular function. If you go to here, you can see that your function named is as CPU timer 0 ISR. What does it mean is it is a CPU timer 0 predefined keyword. So with this keyword, it is calling this particular function. So after every 500 millisecond, this particular code will be served and your CPU timer 0 interrupt count will go on increasing as you put plus and plus here. Okay, and it will toggle your GPIO 31 LED. And as I told you before, it will acknowledge, you need to acknowledge group 1 interrupt because you are servicing interrupt group 1. From here, you can see M interrupt 1. So you are servicing your group 1 interrupt. So you need to acknowledge group 1 interrupt so that your interrupt should keep on repeating. Okay, so after running this code, we'll see in live how this LED is toggling. And I will also show you key where you can see the output of your code. If you just run this code, this is a console window. You can see if certain errors are there, it will show over here. So this is all about execution of your code. You can see from here first your code branch.asm, which is actually this branch is necessary in order to connect your APIs to your main code. So this code branch.assembly language is there. This assembly has direct access to all the registers. So your code will start connecting from this particular branch. Then it will call all the APIs, CPU timers.c, default ISR.c, global variable functions defines whatever function you have defined globally, that particular GPIO IPC, whatever API, it will call one by one. If certain error is there, it will show. Just like that, here I can see that it is asking me to put my TMU hardware support for FP division in a relaxed mode, but it's not an error. It's a warning to me that I can use it in a relaxed mode instead of strict mode. I'll tell you where it is. Okay, so but it is not necessary, so I'm not concentrating onto that. After that, I will just build this code. After building, I'll just debug it by using this insect like button what is showing over here, and it will start running. Once it is dumped onto that particular board, it will show you green button over here. You just have to click on that button. If you click on that button, and if I put here in this expression window, if I put here register information, you can see for enabling real-time mode, you have to click continuous refresh. So from this, you can see your CPU timer interrupt is running, and every 500 millisecond, its value is increasing. You can see from here. Is my screen visible to all?
Yes, sir.
Yes, sir.
Okay, okay. So from here, you can see this is for continuous refresh mode. If you turn it off, you won't be able to see it running. If you turn it on, you will be able to see it running. And then from this particular webcam as well, you can see my LED is blinking. Okay, every 500 milliseconds it will be blinking. So this is how this particular algorithm runs. Okay, whenever you are using interrupt service routine after a certain period of time, okay, it will be blinking your LED like this. So this was the code related to your red LED. Similar code I have designed for the blue LED with the help of this HTTP. So I'll just stop this code for once and I can go to main, and from here I can see that the code is similar to timed LED blink. In this one, what I have done is this is the declaration of any function. As I told you, if you are using that function outside main, you have to declare it. This is the declaration of any function. Okay. After that, you are running your main function from here. You are running your APIs. The procedure is same. I have initialized system control as well. I have disabled interrupts. I have initialized Pi control modules. I have put disable to all other interrupts. I have used Pi vector table. Then I'm calling here timer 0 interrupt as well. You can call timer 1 interrupt as well. Okay, there won't be any problem, I guess. Just go over here. You can just change it to 1. And if I change it to 1 over here, if I change it to 1 over here, we'll see whether it is correct or not. So if I dump this, now it's showing me error. Okay, CPU timer 1 ISR. It's showing me I have undefined this particular thing. I click it one over here. Yeah, I think it's done. So we are doing it on CPU timer 1 timer now. After that, I will just build this particular thing. Okay, and you can see that they are good to go. And in this particular code, instead of red LED, the GPIO 31 was there. I have taken something else, which is GPIO 31 is here. And in that particular code, same thing was there. So I can change it, not a big deal. Let's say I'll just look into the presentation that I have GPIO 34 as a red LED and GPIO 31 as a blue LED. Since we have used GPIO 31, we'll go for GPIO 34. So for using GPIO 34, what we have to do is, I guess I can change it here B, I can change it here 1, then I can go for GPIO 34 and I can change it here GPIO B, I can change it here 34 and from here I can change it here 34. Yeah, it's related to B. So if you are, you know, unaware of this, what you can do is you can just erase this. You can click on here. And you can see over here. Will come whatever GPIOs are related to this particular thing. It will come over here. Okay. So if it is not coming in blue, it means it is wrong. So you have to put it here B. So if it come in blue, it means this instruction is correct now. And then we have acknowledged all the group 1 register. And from here, CPU timer 0, in place of that, we'll put CPU timer 1 interrupt. So we'll just, copy this and we'll put it over here in the expression window so that when we run the code, we'll understand what is happening. So I'll build it once again after all the changes that I've done. It's asking me to reload the file. Okay, then what I will do is I'll debug this. See, if your all these windows are not getting adjusted, you click on this, double click on this particular thing, it will give you full. If you double click on this, it will give you like this. Okay, so it will be easy for you to handle. So once you learn this particular thing, you practice on your own. Once you have your board, it will be very nice for you. If you run this code, you can see from here. Okay, something is wrong. See, when I'm servicing interrupt, it is not showing over here. It means something I'm doing wrong. So I need to look into it. So I'll just suspend this code once again. I'll run it once again to see if any error is there. Because as far as I remember, from this three CPU timers, one timer is there which is used, which you cannot access. Maybe because of that. CPU timer 0 and 2 you can use. Maybe because of that this error is there. So we'll go with CPU timer 0 only. Not sure whether it is 0, 1 or 2 interrupt. I'll look into it and tell you. You can just 0. Okay. I understood what was the mistake. We have not we have not changed it every place. This is TCR bit is very necessary. You can see what is the use of this register. Okay. Okay, still it's not increasing the number of interrupt. Let's see if I've done anything wrong. Okay, we are clearing all of it. We're calling it. Yes. Oh, sorry. See, what I was doing wrong is I have select timer 0 interrupt in order to trigger, and I was changing it to timer 1. That's why the interrupt was not triggering. Because from here you can see that the timer interrupt 1 is having location. Timer interrupt 0 is from 1 subgroup 7. But if I have to use timer interrupt 1, I have to see in this box where timer interrupt 1 is there. Okay, it's not there. It's not listed. So maybe that interrupt is used for servicing your, you know, main CPU only. So you cannot, maybe you don't have access to that particular interrupt. Otherwise, it would have listed with time interrupt 1 or time interrupt 2. So I guess we can use only time interrupt 0 for this particular thing. Since you can see here there is no other interrupt like time interrupt 1 or anything, You cannot trigger that interrupt and use that interrupt service routine. So certain limitations are as well there whenever you are going to trigger any interrupt. You need to aware whenever you're running any code like this. If you're not getting any output over here, we just saw an example that if you're not getting any output over here, you make sure that you're triggering correct interrupt. Okay. So this is the advantage. If you are as well coding with the board, you will get easily that if certain error is there. So I will just change it to timer interrupt 0 again. I will change fine now. So it should run now. Then you should run it again. Yeah, now it is running. And we can see that CPU timer 0 interrupt is increasing. And instead of that LED previously, which we were looking at, a different LED will be blinking now. So from here you can see that my red LED is blinking now. Previously it was blue. So this way you can use in order to, see any particular interrupt triggering and all. So I'll just suspend it for now. So in this one, you can put all the registers over here. You can see its live values. Okay, if it is interrupt service routine, if it is any other register as well. Okay, so every bit has particular use that why we are using it. And if you want to see what this register exactly means, you just have to go to technical reference manual, and you can just if you click on this, download this, and into this technical reference manual. It's actually quite huge manual of 3,600 pages, but you don't need to read that much as I have told you most of the portions which are useful to you. So you just have to look into the registers which is necessary for programming, and you're good to go. You can see it's a huge manual, and I guess it stands for, I guess, 3,000, 2,500 pages. So they have given in very brief, very long what exactly every module means and what is there. But since it is not possible for everybody to read this much, so I've told you how to go for that. So in this one, if you go to Gpio and peripheral muxing as well, so you can see here certain registers are listed over here, and in this register, it is shown key what will happen if you particularly do with that particular bit of the register. Okay, so this is for that if you want to see any register, what is the use of that? You can go to technical reference manual and you can see here GPA Mux1 as I showed you in the presentation. I've taken the snap from here only. So you can see that there is defined pin muxin for selection of GPIO. So these registers are shown over here. If the registers are ELO protected, they will show just over here. ELO protection in the sense if you want to have access to certain register, just like you can see this register that is pi vector table timer 0 interrupt register. So this is a ELO protected register. So if you go into the manual and look for this register pi vector table timer 0 interrupt, so this register will be ELO protected. I want to say is I want to explain this Watchdog CPU. So if you understand once, it will be a little bit easy for you. You can see what I have done here is in this code, there is one header file which is related to project.h, and in this header file, all the predefined function declaration will be there, as I said before. Then you have a function over here which is related to your watchdog interrupt function. So it is servicing a interrupt service routine which is named as wake interrupt service routine. And then you have two global variables in the sense any function in this code can have access to these two particular variables. If I'm writing 10 functions as well, I can have access to this particular variable. So that's why I'm naming it, that's why they have named it here as global variables. Then you have here uint32. What does this mean is it is an unsigned integer which is of 32 bit. So it can take value like this wake count and loop up count can take value from 0 to 2 to the power 32. And since it is unsigned, it will be having only positive values. So your wake interrupt count and loop count, these are two variables I'm defining here for the algorithm. And from here I can see that other procedure to my algorithm remains same, where I'm initializing a system control for clocks. Then I'm disabling all the interrupts, step 2. Then I have a PI control for step 3, that is peripheral interrupt expansion control initialization. Then you have core interrupt disabling in step 4. And then you have PI vector table in step 5, where you have initialization of your PI vector table. Then what you're doing is you're calling a wake interrupt just like you were calling a particular CPU timer 0 interrupt. Like that you're calling a wake interrupt with PI vector table, and it is a ELOW protected register. Okay, it means if you write ELOW instruction only, you can access this particular register. Okay, it will be mentioned in your technical reference manual that which instruction is ELOW protected. Okay, so these inbuilt examples will actually help you in making any code that you in accessing any interrupt service routine, any interrupt. You don't need to look into anywhere. Only C2000 where will give you a great knowledge to that particular thing. Then you have and wake up interrupt ISR. It means you are calling this interrupt ISR interrupt service routine with the help of this and instruction. Okay, then I have initialized these two variables as 0 0, and this is SCSR bit which is related to your watchdog interrupt bit. Okay, right now what you're doing is you're clearing all the bits of this SCSR. That's why you're written here all, so that there should not be any overwriting or any other bit should be present to that particular interrupt. Okay, so what does this particular register means, that also you can see into your technical reference manual. Like I'll tell you that in a minute. So you can see here, as I told you, group 1 and subgroup 8, it's related to your, you can go to presentation, and group 1 and subgroup 8 is related to your wake interrupt. Wake interrupt is nothing but your watchdog interrupt. So from here we are triggering this watchdog interrupt, and we are enabling the PI module with this one instruction, and with this instruction we are enabling group 1 subgroup 8 interrupt. Then this instruction should be must for every algorithm, as I said before. IER enable with with respect to group 1 we are enabling, so we saw it from here as well, by IER1, that group 1 interrupt we are interested in. Then we are interrupt EI interrupt is for enabling your global interrupt. Okay, now there is one counter which is there in this predefined function service dog. So this service dog, in the sense, it's a function which is related to your watchdog timer. Actually this is related to something. When your watchdog is running, your counter will start increasing from certain value, and this is a register in which watchdog counter register in which you are enabling with this 0028. If you convert this into decimal, okay, you will get if you convert this into binary, you will get some values, and that if you put into your this register of all the bits, okay, you are enabling your watchdog. So you can see this. I think it will be greatly clear from this only. So I can just go to this particular register. Okay, from here you can see what exactly that particular bit means, that is also given into this register. Like from bit number 0 to 2 you have a WDPS, that these bits are used to configure your watchdog counter clock rate related to your internal oscillator. Okay, INT OSC. And it has shown here that how much the rate at which you want to run your watchdog counter, that is given with this particular watchdog. Since it is directly taken from your internal oscillator, this dividation is there. If your internal oscillator 1 is there, it should be divided by 512. if you are using it 000. If you are using it 111, then your internal oscillator frequency, that will be divided by your 512 into 64, like that it means. Then you have here 3 to 5 Watchdog CHK register. So this interrupt is there in order to make you understand. You don't have to understand it like what everything means, because it is not useful to you in more way. Generally people go for CPU timer interrupts, so if you understand that only, it is better for you. Okay, these things is there if you want to, you know, use this Watchdog interrupt. Okay, so the procedure will be same. In order to enable Watchdog, you have to put 0028 as in front of WDCR. Okay, after that, so you don't have to, you know, waste your time in deciding whether what will happen if I put 01 here. Okay, TI has already given you facility that you go through this procedure, you will be able to trigger an interrupt. So what I want to show from this example is when Watchdog interrupt is triggered. Okay, so what will happen is your wake count will go on increasing. Okay, and when you uncomment this service dog, whatever wake interrupt over here, if you uncomment this, what will happen is this function will keep on running and your loop count will only increase. But if you comment this particular thing, then once it will come to loop count and then it will trigger your wake interrupt. So what I'm doing is, if I run this, sorry, so if you play this, you can see here right now both of the loop count and wake count, which are my variables, they are increasing. Why it is like that? Because what is happening is this for double semicolon is for your infinite loop. Okay, even if there are certain instructions such as while one in C that you can use for your infinite loop. So whenever this infinite loop is there, it does not have any purpose. It's just there whether your microcontroller is going into your main function and executing all the instructions or not, for confirmation of that only. So we have just taken one variable loop count and we are increasing that variable with certain plus sign. As you know, plus in C will increment that particular variable by 1. So this loop will run infinite times. Once this microcontroller start, or once this program is debugged onto this microcontroller, this loop count will go on increasing. And you can see in this example your wake interrupt service routine is being serviced, and that's why your wake count is as well increasing. So you can see here that is increasing at particular rate, and your loop count is increasing at a much higher clock rate. Okay, so you can see with this that your wake interrupt is servicing at a certain period of time, but your loop count is running at a very fast rate. It means it is running at your main CPU clock, and wake count is divided by certain, you know, PLL, so that your clock frequency should reduced and your ISR should be serviced. Okay, but we don't have a time here with this instruction, like what particular time it should run. So if you disable this, what will happen is, okay, if you stop this and if you build this once again by uncommenting this particular function, which is service talk function, which is related to your Watchdog interrupt. So what will happen is, once it comes into this infinite loop, this service dog is used for resetting your Watchdog counter. So every time it comes into this loop, it will call this function, and this function will actually reset your Watchdog counter. So reset Watchdog counter means your Watchdog interrupt should not happen, and your code should be running into this particular loop only. So it will come to this loop, it will take this function service dog. Once this call is executed, it will come here, it will reset the Watchdog counter. So it will not go to this particular function. Okay, from here if I run this, you can see your wake count is at 0 now, but your loop count is increasing. So it means that every time it is coming to this particular loop, to the service dog it is calling, this is a call to function, and when service dog is being called, it will reset your Watchdog counter. This instruction particularly is there in order to reset your watchdog counter. So certain watchdog key register is there in which certain value has been put, so that in order to reset your watchdog timer. Okay, so it is like this. I hope this is clear to everybody. Okay, this is just to explain you the execution of an interrupt. How does it happen?